All right, pre-calc, good afternoon. This is going to be kind of the first video, and this is going to be one of the few videos where I actually walk through the notes with you and kind of read the book a little bit. It's not going to be as thorough as I originally intended it. I'm kind of losing my voice. So I'm just going to kind of walk through the notes. I think it's just one page of notes on day one, and just go through the examples with you. So, 9.1 day 1 is on sequences and series, and it's kind of just an intro into sequences and series. So the first thing they want us to figure out in this notes right here is what's the definition of a sequence. So let's go to our book, let's go to our notes and read a little bit, see if we can figure out what that is. It says, in mathematics, the word sequence is used in much the same way as in ordinary English. Saying that a collection is listed in sequence means that it is ordered so that it has a first, a second, a third, and so on. So it gives two examples. There's like the sequence that's just 1, 2, 3, 4, and there's a sequence that's 1, 3, 5, 7, and it just goes on and on and on. Mathematically, you can think of a sequence as a function whose domain is the set of positive integers. So, I mean, really what sequences are is they're functions that they take the integers to a particular set of numbers. The functional definition of a sequence is maybe a little bit more complicated because really, in the core of it, a sequence is just an ordered list of numbers. And so that's what I'm going to write down for my definition. I'm just going to say a sequence is an ordered list of numbers.
Tammy, please report to the office.
So
Tammy, please report to the office.
Normally how we kind of like denote a sequence is we'll say it's like A1 is the first number in the sequence. A2 is the second number. A3 is the third, and so on. And so that's when we say it's an ordered list of numbers. Okay, it wants us to read through example 1 and then try exercise 9. So let's go over to our book and see what example 1 is. So example 1 is just showing you how to write the terms of a couple sequences. So like the first sequence it gives you is a of sub n is equal to 3n minus 2. And the second sequence it gives you is a sub n is equal to 3 plus negative 1 to the nth power. And you can see for each of these, it's just writing the first, second, third, and fourth terms. And so you can see how it says a sub n, and then in the formula itself it has an n. It's basically just matching up which term that is. So if you want to find like the third term, you just plug in 3 for n, and that's really all you do. So like on a sub 4, we just plug in 4 to the formula that it gives us. Let's just try an example problem to get clear on that. It wanted us to do exercise 9, I believe, in the book. So I'm going to scroll down to our exercises.
Tammy, please report to the office. Tammy,
okay.
Please report to the office.
So it wants us to do exercise 9. Exercise 9 is a sub n is equal to 2n plus 5. And it wants us to write the first 5 terms of the sequence. So a sub n is 2n plus 5. I'm going to write that down really quick. So if we want to calculate a sub 1, we need do nothing other than just plug it in. So a sub 1 in this case is just equal to 7. A sub 2, we need do nothing else than plug it in. So a sub 2 is equal to 9. A sub 3, again, we're just plugging it into the formula of our sequence. Equal to 11. A sub 4 is equal to 13. I hope this is pretty straightforward for you and you don't let the functional definition they give of sequences kind of like be intimidating. A sequence is just an ordered list of numbers, and you figure out what a sequence is by looking at the rule that tells you how do you compute the particular terms in, in any given sequence. And so for this one, we computed the first 4 terms. We got 7, we got 9, 11, and 13. And this just keeps going on forever and ever and ever. But those are just the first 4. If we read down in the notes a little bit, we'll see that it says example 2 on the top of page 641 shows us an example of an alternating sequence. Read through example 2, then try exercise 25. So let's read through example 2 and then try exercise 25. We're going to learn about alternating sequences, and again, that's just a different kind of sequence. I got to scroll back up. Hopefully this is a little bit easier for you. You can just have your book out next to you while you're doing this. Okay, here we go. Example 2. A sequence whose terms alternate in sign. Write the first 5 terms of the sequence given by a sub n is equal to -1 to the n divided by 2n plus 1. So I mean, this is just like the sequences we saw in the first example, except on this one we have that -1 to the n on top. And if you look through your book, you're going to see how that -1 to the n is going to make the signs on each of the sequence terms alternate. So that's why we call this an alternating sequence in your notes, because that -1 switches the signs. So, I mean, you can read that in your book, but now it wants us to try exercise 25. So I'm going to go to exercise 25 and see if I can work my way through it. Okay, here we go. Again, we're in the same kind of problem set, so it wants us to write the first 5 terms of the sequence. So 25, a sub n is equal to -1 to the nth power divided by n squared. So a sub n is equal to -1 to the n divided by n squared. And again, if we want to find the first few terms of the sequence, we need do nothing other than plug in whatever sequence term we're trying to find. A sub 1 is -1 to the first power divided by 1 squared. And in this case, that's just equal to -1 divided by 1, so just -1. A sub 2 is equal to, again, just plug it in, -1 squared divided by 2 squared. So now on the top, -1 squared, well, that just becomes a positive 1, divided by 2 squared is 4. For a sub 3, we just plug in 3, -1 to the third power, all over 3 squared. -1 to the third power, now we're back to -1. So -1 all over 3 squared is 9. So the first, I kind of ran out of room here. You'll have more room in your notes, but our first 3 terms are -1, 1/4, and -1/9. So in the first one, it was kind of just a straightforward sequence. This one's an alternating sequence, just a little bit different. I hope these beginning parts of the lesson are easy enough for you. It's kind of the later problems in 9-1 that can be a little bit tricky. So I'm going to erase what I have in the notes at this point because I need to scroll down, and for whatever reason, it doesn't let my writing scroll with it. So let's scroll down really quick. Okay, so it says the top of page 642 gives us the definition of a recursively defined sequence. And then the question I asked you here is, what is a recursively defined sequence? How is it different from the sequences on the previous page? So I need to actually go to page 642 now to figure out what these recursively defined sequences are. Where are we at here? Okay, 642. It says some sequences are defined recursively. To define a sequence recursively, you need to be given one or more of the first few terms. All other terms of the sequence are then defined using the previous terms. A well-known recursive sequence is the Fibonacci sequence shown in example 4. So, I mean, really all that recursive sequences are sequences where you can't find the next term unless you know all of the previous terms. So like, for example, if you look at example 4, it says the Fibonacci sequence, recursive sequence, and it says the Fibonacci sequence is defined recursively as follows. A sub 0 is equal to 1, so the 0th term is 1. A sub 1 is equal to 1, so both the 0th term and the first term are equal to 1. And then A sub k is equal to A sub k minus 2 plus A sub k minus 1, where k is greater than or equal to 2. So this last part here, they're telling you the rule for the sequence. If you want to find the kth term, you just add the k minus 2 term and the k minus 1 term. And in plain English, that just means if you want to find a term, you add the two terms that come before it.
Cami, please report to the office. Janet, Cami, to the office.
Okay. So the Fibonacci sequence is one example of a recursively defined sequence. You can see it in action down here. So you know that A sub 0 is 1, A sub 1 is 1. If you want to find A sub 2, you just add the two previous terms. If you want to find A sub 3, you just add A sub 2 and A sub 1. If you want to find A sub 4, you just add A sub 3, it comes from here, and then A sub 2 comes from here. So that's all a recursively defined sequence is. The question I asked you here is, what is a recursively defined sequence? So we'll say it's a sequence. I'll say it's a sequence where each term is dependent on the previous terms. I hope you see what I'm doing with like these questions I'm asking you in the book. When I say like what is the definition of a recursive sequence, to a certain degree I'm asking you to make sense of that in your own words. So like here, I didn't take their exact definition. I read their definition and I thought, okay, how does that make sense to me? To me, it seems like a recursively defined sequence can be best described in this way. It's a sequence where each term is dependent on the previous terms. The second question I asked you here is, what is a recursively defined sequence? Okay, how is it different from the sequences on the previous page? And the difference really is that on the previous page, if we wanted to calculate like A sub 3, we didn't need to know A sub 2 or A sub 1. So the difference between a recursively defined sequence and the other sequences is that for the others, you don't need to know the previous terms. And that kind of makes recursively defined sequences a little unique. The previous terms. So there are certain frustrations using recursively defined sequences where like you can't figure out like the 200th term without knowing all 199 before it. And as we go further in the chapter, we're going to find better ways to deal with recursively defined sequences. Okay, it wants us to read through example 4, then try exercise 85. Example 4 was just the Fibonacci sequence one we looked at a minute ago. So I am just going to go straight to exercise 65. I do need to erase all this stuff here. Oh gosh, what just happened? Okay, here we go. Okay, exercise 65 wants us to write the first 5 terms of the sequence that's defined recursively. So, 65, it says A1 is 3, so I'm just going to write that here. A1 is equal to 3, and then A sub k plus 1 is equal to A sub k minus 4. And again, in just plain English, that means the k plus 1 term is equal to the one before it minus 4. So every term is just the term before it minus 4. Let's see what that's like in practice. So A sub k plus 1 is equal to A sub k minus 4. So if A sub 1 is equal to 3, that means A sub 2 is equal to 3 minus 4, which is negative 1. That means A sub 3 is equal to, okay, here, A sub 2 is negative 1, so A sub 3 is negative 1 minus 4, which is equal to negative 5. The next term in our sequence, A sub 4, it's equal to, what was the previous term? Negative 5. Subtract 4. Negative 9. And our last term that we need to find, A sub 5, is equal to the previous term, negative 9, minus 4, which is negative 13. So those are the first 5 terms of your sequence, negative 1, negative 5, negative 9, negative 13. Or I guess I forgot about A sub 1 back here, which is 3. So the only difference between recursively defined sequences and the first sequences we looked at were that recursively defined sequences, you need to know the terms before. Okay, the last topic for day 1, I believe, it wants you to read through the rest of page 642 and the top of page 643, which tells us about factorials. I'm not going to do this reading. You can read through it on your own. But the question I asked you right here is, what is 4 factorial? And if you've read through the notes or whether or not you haven't, 4 factorial is just 4 times 3 times 2 times 1, which if you do that, it's equal to 24. If you didn't understand what the factorials were on the previous page, if you take, some number factorial, let's say, 8 factorial, well, that's just 8 times all the numbers less than it, but greater than 0. So 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's all factorial means. Factorials are used a lot in sequences, which is why they're introducing them to us here now. That's all factorial means. The next thing I have here written in your notes is that the middle of page 643 shows you how to evaluate sequences in a graphing calculator. I'm not going to require you to do this, but this might make some of your future calculations with sequences easier. So it might be easier for you to use the functions of the graphing calculator to figure some things out. The middle of page 643 shows you how to do that. I'm not going to go through that, and it's up to you if you want to do that or if you want to do it by hand. Okay, I believe this is the last thing we need to do. Yep, okay. So it wants us to do exercise 81. But before we do that, we want to read through example 6. So I'm going to go to example 6, read through that really quick, and then we will go through that exercise. Okay. In example 6, it's just having us evaluate factorial expressions. So there's not even really anything here with sequences. It's just having us do a little bit of number crunching. So you can see in A that it's 8 factorial divided by 2 factorial times 6 factorial. So basically they just wrote all these numbers out. They wrote 8 factorial out up top. They wrote 2 factorial out, and then times 6 factorial. And then you can see what they did. They didn't actually punch all those numbers into their calculator. What they did was they canceled. They saw that they had 1 through 6 on top, and they had 1 through 6 on bottom, so they just canceled them. And then what they were left with was 7 times 8 up top and 1 times 2 on the bottom. You can read through that more closely, but it's the same thing with B and C. They just write out 2 factorial and 6 factorial. They write out 3 factorial and 5 factorial. And then they cancel what they can. So I tell that to you, like when you're computing factorials and things like this, you don't actually want to throw all this into your calculator. Before you do that, you want to see what is going to cancel and what isn't. And let's see an example of that in exercise 81. So I guess I gotta go to exercise 81 here. Where are we at? Okay. In exercise 81, it wants us to simplify the factorial expression. So just what they were doing in the last example. And the factorial expression it gives us is n plus 1 factorial over n factorial. And so this one's a little bit different because there's no actual numbers involved. So let's see where we at. So n plus 1 factorial over n factorial. So yeah, no numbers involved, just n, some generic number n. So the first thing to do would be kind of to write out what n plus 1 factorial is. And it's pretty simple. It's just n plus 1 times n minus 1 times n minus 2. But now you're seeing the problem here. We don't actually know what n is, so we don't know how far to go down. So what I'm going to do is say ... all the way till we get to 2 times 1, because that's where factorials end. So it seems like that might be the problem, but when we write out what n factorial is, we're going to see how nicely this works out. Well, n factorial is just n times n minus 1 times n minus 2 all the way down to 2 times 1. So you can see how nicely this works out. Everything cancels except for this lone n plus 1. So n plus 1 factorial divided by n factorial is equal to n plus 1. That's kind of the substance of what we want to do for day 1. If this was, too slow for you, I hope you sped up the video. If this is too fast for you, I hope you slowed down the video. I mean, again, this isn't an excuse to not read. I just hope this is helping you in your reading. See how you can kind of take the parts of the book that are helpful to you and leave the parts that aren't. Help you to come and understand things. I mean, at this point, it would be good to scroll down a little bit. What still doesn't make sense about the reading for today? Write down questions to ask your peers or teacher tomorrow in class. So anything that doesn't make sense, you should really write it down at this point, and we will talk about it on Monday. Okay, I hope you're all having a good week.